Okay, welcome to our podcast, Bertil. We are very happy to have you here, and it's an honor for us. First of all, I would like to have a brief introduction. Could you please briefly introduce yourself and provide us with your background in the field of laboratory accreditation?
Thank you very much. I'm very honored to have all laboratories listening to this who is interested in accreditation. My name is Bertil Magnusson. I work as a consultant for laboratories, supporting them with quality and laboratory accreditation. I have a small website, which is called www.trollboken.se, where you can find a lot of information. My background is analytical chemist. I worked out in the industry for about 20 years, and there we started with accreditation already in the 90s. And then I also worked 20 years for the National Measurement Institute in Sweden, where I represented Sweden in the international collaboration within the SI system.
Okay, thank you very much for the introduction. As we have already talked about that today, we are going to talk about measurement uncertainty issue. And first of all, I would like to ask that it has been already 20 years since ISO 17025 was published for the first time, and the laboratories have been dealing with this issue. What is your opinion about the current status of this complicated term for laboratories, and they have been dealing, there have been lots of disagreements about that. Could you please tell us your opinion?
Yes. Estimating measurement uncertainty is not easy. Already back in the 90s, where most of the laboratories tried to model the data to get estimation, we got an underestimation of measurement uncertainty. But in fact, still we get an underestimate of measurement uncertainty. And this, I would say, is mainly due to three important issues. The first one is that the bias can vary within the scope of a method. For a method can have different matrices, for example, salt water, groundwater, and the matrix can make a difference. So if you then measure your samples, reference samples, you get a bias for that matrix, and that can vary from matrix to matrix. For example, if you have a method for steel, you can have one for high and low alloy steel, and you can get different biases. There is today no good approach, or very few, on how to include that variation in the method. And if you don't do that, you will underestimate your measurement uncertainty. The second is that it's very difficult to model the situation. We need experimental data, because we will have variation over time. We will have, for example, different matrices, different persons, instrument in different conditions. All this has to be included in the measurement uncertainty. Mm-hmm. And the third is that we need time. We want enough time to, I would say, get at least 60 data to include all the variation within a laboratory. And that, in fact, means that you cannot get a real estimate of measurement uncertainty when you start a method. You need to wait 1 year. But we can, of course, give a preliminary measurement uncertainty.
Okay, thank you very much. We will touch this modeling versus experimental approaches later in our interview. But in the 2017 version of ISO 17025 standard, the term estimation has been changed to evaluation for measurement uncertainty. I was listening to a video produced by one of APAC trainers, in which she said that by evaluation, we mean that the laboratory should not be merely calculators of uncertainty. At the end of this process, they have to evaluate how big or how small is the uncertainty, and would it be fit for purpose? By replacing this term, we would like to take their attention to this. Do you agree with that, or do you think it means something else?
No, I think what this person said is you have to be humble when you do it. And but in fact, I would say that we can talk about quantifying uncertainty, calculating uncertainty, evaluation uncertainty, or estimating measurement uncertainty. So both these terms are used and can be used, but still we have to be humble that it is difficult, and when we come up with a measurement uncertainty, we should compare it with other laboratories to see if our uncertainty is realistic or not.
Mm-hmm. You mean to have a target uncertainty value and compare the calculated one with this target measurement uncertainty and evaluate if it meets the requirements of target measurement uncertainty? Is this something like that? Or no, just estimate it, have some value and report it when it is required?
Well, target uncertainty is what you need. But I think here we're talking more about that you get an uncertainty and you want to compare if it's realistic. One example is if you go to an ISO standard and you find the reproducibility data there, that you can use for comparison. And that is also described in the NORTEST approach, how to do that.
Mm-hmm. Okay, thank you very much. Bertil, you are one of the authors of the famous NORTEST report 537. Which is, I think, the main source of top-down approach for calculation of uncertainty. I have read it several times, different editions of that, and it has been very useful for me. But could you please briefly summarize what is the approach in this document?
Okay. I think for any measurement uncertainty estimate, you need to specify what you measure, if it's total or solid or leachable or whatever. And the second is you have to tell the scope of the method. So which matrices, which concentration range you need to have. The NORTEST approach also needs extensive validation data, quality control data, and also, of course, maybe proficiency testing data. But you also need to know how the standard deviation or the uncertainty varies over the concentration range. And in most cases, you will have one for lower and one for higher concentration range. And then from this data, you in fact estimate two components. The first one is the within lab reproducibility, which is a bit difficult to pronounce. And that is, for a client to your laboratory, is the variation he would see if he give you the sample in January, March, and September. That is the variation we need to estimate. And the second one is we need to estimate the possible bias for our different matrices. Mm-hmm. And these two together will form the measurement uncertainty.
Okay, thank you very much. Okay, let's go into details of this approach. Many people, many experts criticize that when we use this approach in order to calculate or estimate our measurement uncertainty, the systematic component of measurement uncertainty is too low, because typically we expect that systematic errors should be corrected and the residual value should not be considerable. But using this approach typically gives a rather high estimate of systematic component compared with modeling approach. What would be your answer to these critics?
Well, I think that in one example they are correct. If the bias is higher than your within lab reproducibility, within the variation in the lab, then NORTEST will overestimate measurement uncertainty. But I think that if you have such a high bias for one of the matrices, you should divide your method into two. Mm-hmm. So you should not have such high biases. But in many cases, we still have some bias, even if it's small. And we need to take that into account. And as already described before, the problem is not overestimating. The problem is underestimating. But you're right. People who come to our courses, they come with a low uncertainty, and then we include the bias. And then after having a 2-day course, they come up with a higher uncertainty. And they are always not content. But I think they come up with a more correct uncertainty. So
Okay,
you
thank you
have
very
to,
much.
you have
Okay,
to.
please go on.
Okay, please go on.
I would like to say that you mean that overestimating measurement uncertainty would be safer rather than underestimating it for further decision that would be made based on the measurement results. Am I right?
Well, I would not say that we should focus on that, but if we underestimate the measurement uncertainty, then we can have wrong conclusions. So I think it's very important that we try to get a correct uncertainty, and maybe slightly higher if that was you intending. That is.
Okay, okay. Thank you very much. The other issue that I would like to talk to you about for calculation of the systematic component of the uncertainty in this Nortest document, you introduced 3 different approaches using certified reference materials, use the data from PT participation and the recovery studies. For PTs, in many PTs, the consensus value of participants is used as the assigned value that might have its own systematic error. And basing the calculation on this assigned value in order to have an estimation of a laboratory systematic value might not be correct. What would be your answer to this critic again about this approach?
So your question is, how reliable is the consensus value in the PT? Well, the experience shows that they are very, very reliable, provided that you have many members, many delegate participants. So I would say if you have more than 30 participants, they are in most cases very, very reliable. There are some cases where we have problems, and usually there is when there is a problem with the analyte. I can just measure 2 examples. If you have measured tin in tomato paste, we found that the consensus value was actually too low when we did reference analysis for that. And this is because tin is an extremely difficult analyte to handle. And then another example is if you want to determine chromium, total chromium in a silicate or a solid, you need hydrofluoric acid. And if you don't use that, you will get too low value. So if all the labs just use aqua regia for determining the chromium in a silicate matrix, of course, you will not get the total. But you can also think about what you define. If you define the leachable, then it's correct. So I think this definition of measurement is very, very crucial when we talk about measurement uncertainty.
Okay. Thank you very much. The other question is that in many of reference literatures, especially the ones who describe the modeling or bottom-up approach, they come up with a term type A uncertainty for the random component of the uncertainty. And in many of them I noticed that they said that you should repeat your measurements under repeatability conditions in order, or they only use the term repeatability in order to show how this type A component should be estimated. But in your Nortest document, you clearly say that the measurements should be performed under intermediate or within laboratory conditions in order to have a realistic value of random effects. What do you think is that the difference in these 2 approaches?
Well, I think you already answered the question, my friend. Of course, repeatability will only give the small variation within 1 day and not the total variation. And this is actually mentioned in the ISO we could say, Bible for measurement uncertainty, the GUM. They say that you need also to look into the time variation. So I think this is very simple. We need to include all the variation in order not to underestimate.
You mean that we have to evaluate the time-to-time variation within the laboratory and not only consider the repeatability variations. And in that case, we will again underestimate our type A or random component. Am I right?
Yeah.
In any approach,
I mean,
both in modeling or top-down approach, it doesn't make any difference for type A evaluation.
No, absolutely not. And of course, for some physical measurements where you have very stable instruments, maybe the time variation is very low, but we need to look into it.
Okay. The other question is that it has always been a question for me that when we would like to calculate the bias component in using a north-test approach in the laboratories, we accumulate and combine both negative and positive biases together and accumulate them. Sometimes this having positive bias in one round of a PT and having negative bias in the next round are due to random errors in the laboratory, not systematic ones. But when we would like to calculate the bias component of measurement uncertainty, it doesn't make any difference for us if it is a positive bias or negative bias. We combine them all together, and sometimes it seems that the final value is rather large. What would be your comment about this?
This is really a problem for the north-test approach, because we talk about a bias. That means that we need to measure this value not once but several times. So if you have a CRM, it's easy. You can measure it over a longer time period, maybe at least 6 to 10 times to get a better value. I would recommend that you usually measure the PT samples several times to get a better mean value from the lab. But this is a problem that you can overestimate. And I would usually recommend that if you have, for example, 10 rounds and one is totally out, you need to take that out. You have to consider taking that out to calculate the measurement uncertainty, because otherwise you will overestimate. So I think you're pointing to a very critical issue. But if you could measure your PT samples more times, you could get rid of this a little bit.
Okay, thank you very much. But I remember something during one of our assessments in ISO 17043. We used to give laboratories, we organized PTs in the field of water and wastewater. We used to give them samples in a large quantity in order to provide them with a sufficient sample in order to repeat the test several times. The assessor noted an observation that PT should reflect the actual situation of the lab. For the routine test samples, they don't repeat. Your PT test sample should be small enough in order to let them repeat it as routine samples, so there would be no chance to have a sufficient sample in order to increase your replicates.
Yeah, this is absolutely correct.
Yes.
So a PT sample should, for that purpose, give a reflection of the laboratory's competence that day. But if we need to use the PT data for measurement uncertainty, we would be very valuable if we could repeat that measurement over a longer time period to get a mean value. So you are pointing to a very critical issue for the north-test, and I think we have to be humble that it's not so easy.
Yes, I understand that sometimes it's not very easy.
Remember, I think that, in my opinion, you shall always start with getting a CRM. And then you just use the PT more like to see that, yes, my measurement uncertainty was correct. So I would recommend in all cases, if you can get a CRM, to use that. And that is what we would normally recommend as the first And then you just use your PT to check your measurement uncertainty estimate.
Okay, okay. Thank you very much for your comment. The other question is that your Nortest document title, I think it's for environmental analysis, and in other similar documents, it seems that this top-down approach or experimental approach should only be used by chemical laboratories. What do you think? The concept seems to be applicable for other laboratories who perform physical or mechanical testing too, because they have some certified difference materials in order to estimate the bias component. The random evaluation seems to be similar to the chemical analysis. Do you think this approach can be used by those laboratories too, or no, it should be limited to chemical analysis?
Absolutely not. If you have quality control data and you have a good estimate of your bias between different samples or sample types in your method, you can absolutely use this approach. And we have used it for a lot of different industries and a lot of different sectors. So we use it a lot for physical testing also. But I think, if I might say something, the most important thing when we measure measurement uncertainty is not the statistics. It is that you know your method and you know your samples. That we always have to highlight and remember. So that knowledge, for example, if I'm talking about blood analysis, of course I need a doctor to know something about how to take the sample and know about the problems. And you need an analytical chemist who knows about the method. So these knowledge together we need to estimate uncertainty, not just the calculations or evaluation.
Okay, okay. Thank you very much. My last question is that I was reading a paper in which it says that we cannot consider measurement uncertainty as a performance characteristic when we perform method validation. It is a property of a test result. And in method validation, we should focus on method performance characteristics like repeatability, reproducibility, linearity, specificity, and other characteristics. Do you agree with such a comment, or no, measurement uncertainty? I myself believe that measurement uncertainty is a very important performance characteristic which shows the quality of the test performed in laboratory. What would be your idea?
Well, of course, it's correct that a measurement uncertainty is a property of a test result. I mean, of course, that's what we are talking about. The second issue is, of course, can it also be a property of a method? I would normally recommend that when we talk about method validation, that is also the approach that EURAChem uses, that we have method validation where we look at the method performance and compare that with some kind of requirements. Then we can use this data together with quality control data to measurement uncertainty. So to estimate measurement uncertainty. So that is another step, I would say. But can then measurement uncertainty be a property of a method? Yes, it can be that. But we have to remember that that is then for normal routine samples. I am very favor of duplicates, because when we are working, as I'm working at the National Measurement Institute, we get a lot of samples that is unknown to us. So we always take duplicates. And then we compare that difference. Is that difference small enough, what we normally would expect? And we take that criteria to decide if we can use the uncertainty that we normally would report for that method. That is the order. Yes, please.
You mean that to check the difference of duplicates against measurement uncertainty to see if we have a small and negligible difference? Am I right?
Well, I would say that this is of course a repeatability limit, we call that, the difference between two samples. And from the repeatability you have in your lab, you can calculate that. So you, for example, you maybe have a measurement uncertainty of 10%, but we know that the repeatability limit should be less than, say, 4%. So then we check for all the samples we get, we check, is the repeatability limit less than 4%? Yes. Then we can certainly report the normal measurement uncertainty. If we then get a very inhomogeneous sample, like we get a repeatability limit of, say, 20%, then we cannot report that uncertainty. We have to talk to the client and say we have to have a higher uncertainty, or we have to make more measurements because the sample is so inhomogeneous.
Okay. Thank you very much. There is no other question from my side. Would you like to add something to the discussion?
I would just want to add again that for measurement uncertainty, of course, you need the data, the quality control data. You need to have the variation over the bias, but you need to know your method, and you need to know your samples, and that is the most important thing to get a reliable estimate of measurement uncertainty. I wish all the laboratories good luck with this very difficult task.
Yes.
Thank you very, very much.
Okay, thank you very much, Bertil, for your time. It has been a pleasure for me to have you in our podcast, and I hope that you stay safe and healthy among this time, and I hope to see you again after this pandemic over, and wish you a healthy time. Thank you very much.
Thank you very much.